front running is actually really kind of fascinating just because it's essentially a really clever way of using almost insider trading techniques, using non-public information to your advantage. A lot of this relies on having visibility into mempool. Now, everybody knows you made a transaction, it goes into mempool, sits out there waiting to get put into a block. And it can sit in mempool for hours on some kinds and different forms of transaction, especially ones that have low gas or just aren't really going to be worth a whole lot of money to whoever's ever writing the block. So you can actually do some really cool stuff with this attack. And because of the specific nature of contracts, this is a really hard one to kind of protect. It's a really difficult nut to crack. The interesting part, though, is they called it a race to order chaos for the winner. And I like that just because it's a race to get first in line to get whatever product it is. And again, that information flow, especially in financial markets, taking advantage of the volatility of Bitcoin or of Ethereum or anything else, you can get some really interesting intermediaries who can make a profit by being first to know about a thing and act upon it. And this works for domain registries, works for some of the early stock market deals, whois gateways. These are really common applications of this whole process. And it's like when I go and I want to buy a domain, I'm going to turn around, and if I use the domain finder from the hosting company that I use, if I don't buy it right away, if I try to think about it even for like 10 minutes, someone else will come along and buy it. And then they'll say, oh, we'll just give it to you for $1,500 instead of the $29.99 for the .io that I was really looking at. So someone has that visibility into Dan's looking for a no domain today, and I'm going to go buy it out from underneath them. That is really what a front-running attack is. If you are a stock person, when you're buying stocks, and you're using pricing, sometimes the price you buy at is not the price that it was when you made the order because of the way that the information in that I bought 100 shares at $12.95. Well, I really honestly paid 14 for them because something happened along the way. There just weren't any shares available for $12.99. So someone knew that there's a big buy going on and was able to increase the price on that. And again, it's that non-public information to their advantage. It's knowing that someone's going to want something and then being able to either manipulate the price or take advantage of supply and demand to make whatever you're going to do. Now, there's three kinds of ways this actually happens, and there's displacement, insertion, and suppression. So these are really interesting because they're all kind of similar, but take a different vein on this one, right? So essentially, displacement is first to market. I need to get my order in or my bid in before you do, right? So the example here is we're bug hunting. I find a bug. It's a really cool bug. I share it with my friend. My friend turns around and steals it and submits it first before I can. So my friend will get all the rewards for finding that bug, and I will no longer have a friend. So for this attack to happen, I have to manipulate the gas price and put a higher gas price, what I'm willing to pay for that transaction, to be validated and stuff into a block. And that means it has to be to my advantage to getting there first, like a bug hunt for $10,000. If I pay an extra $15 in gas pricing, then that's higher than the network average. I still make some money. I make some really good money on this. I may lose a friend, but I make some good money on it. And again, these are things that are going to happen. Now, this is another one I like. It's called insertion. So what I want to do is I want to manipulate gas price so where transaction assets, this is where order matters, right? So I always use coffee producing in Peru. I have Juan and Bob and Jim. So on this one, let's say Bob and Juan have a contract to do coffee, and Juan and Bob agree to a price, $1 per bushel. Now, if Jim comes along and offers a better price to Juan, there's nothing that says Juan has to buy that coffee from me at $1 per bushel. If Jim is offering $1.25 or $1.10, something to make this really worth to Juan to break that contract or not sell through my contract and go through Jim's contract. Now, if Jim corners the market on Peru coming in from coffee, then Bob has to go to that higher price. And Jim, if he's cornered the market on Peru, could go, hey, you're going to give me $2 per bushel for coffee. So Jim makes money off the difference in prices. And Jim needs to understand that coffee price in that contract, which if not concealed is sitting there waiting in the transaction, right? Unencrypted, just waiting, hanging out. Here's how much I'm paying per bushel. If Jim knows that, he can manipulate the price of coffee. The other one that was interesting too, especially when you have order transaction dependencies, right? You can get some really interesting race conditions. Like, say, for example, a withdrawal transaction can be front run to a change in the reward function call, right? So if the reward function call is done right, you can sit there and keep on punching that reward function call button and keep on withdrawing money until that whole thing is gone, until the whole pool is gone. So if one function sets the reward percentage and then another one uses it for withdrawal, you can really alter the output of that contract and get it into a race condition where you're just pressing the cash register button until that contract is empty. And once you have an empty contract or a race condition like that in a contract, it makes it really hard to go back and use it on the blockchain. This one I like too. This one's suppression, because basically what you're trying to do is you're trying to corner the market, right? It's called block stuffing. And you're trying to get your transaction to the validation point first. So you delay the opposition, basically whoever else is in that pool with you. Now you can do this asymmetrically or you can do this in bulk, but it all has to do with gas price and gas limit. And what you want to do is get a good gas price, make it so that it hits the gas limit on that block and has to be really worthwhile to get it there. So your transaction goes first, right? Now we see this sometimes with the asymmetric where you're trying to cancel the order while it's being fulfilled. You see this a lot with digital goods. I'll go in, I'll buy a thing, and then I'll cancel the transaction after I've downloaded it. And if I can get those two transactions into the block first, the person who sold me the good will never see a dime for it. So kind of asymmetric. It's not a new attack. It's just kind of an interesting way of approaching it. And then the other one is bulk, trying to purchase a limited set of items by multiple people. So say you're trying to buy tickets to PAX. PAX tickets always sell out, and it always sells out to bots. And you have a limited amount of tickets to PAX that you can actually get, especially if you want the 4-day tickets, right? So if you're trying to purchase a limited set of items and there's a lot of people in there, someone comes in and hoovers up as many of these tickets as possible, 4-day tickets to PAX, and then you're kind of stuck. If you want tickets to PAX, you now have to go off market. You have to then pay inflated off market prices. And you don't even know if you're going to get a guaranteed ticket from PAX. So bulk is really interesting, just trying to hoover up as much of the product as you can. This works great for tickets. This works great for some kinds of NFTs, right? If you want to definitely basically corner the market for something you think is going to be a valuable NFT. It is super common to see this. Again, if you can do it, why not? People are kind of have that moral movement. They may not be where you're at. So you have to remove the benefit of front running from your application, and mainly by removing transaction ordering or time as a factor. So your programming code has to reflect that transaction ordering happens and then you're not using time as a factor. So markets, for example, from batch auctions, which is also to protect against high frequency trading concerns. Make sure that when you're doing auctions that someone can't manipulate the time to get in there earlier or can't see the transaction, so they don't know what the high bid is right now. And that's where pre-commit schemes come in. And I really like pre-commit schemes because they don't really go into mempool. They're not waiting as a transaction. They're waiting either off-chain on this to be pre-committed. So if I say I'll pay $1 for this, that can get wrote into an array, an off-chain data array, and hashed. And that odds are likely no one's going to ever see that. And it will stay there until actually done. Now, when the auction's finished, I can pull that information from the off-chain array, drop it into the transaction log, and boom, I've won. But no one knows what I bid on. And pre-commit schemes are really good for this because I have my data off. I know what it is. I can hash it. I can salt it. I can do what I want to do with it. I save money on gas because I'm storing it over here on my side of the fence. And then when I finally have a winner, I can throw it over the wall as a transaction, and then it's visible to everybody. It's also possible to limit price slippage by putting inside of your array that minimum or maximum acceptable price trade on a range. And that will also reduce the cost of front running. And that's essentially using the high, low, medium, time-weighted average that you can do here. So it's really kind of nice to have these options to you, and you're going to want to make sure that you approach these, right? Now, this is really common too when you're using this as a liquidity pool. So if you are working with a low liquidity pool, something that doesn't have a lot of movement, it's possible that you can get less than you thought once the trade is finalized. Now, the reason for that, you have a low liquidity pool. When you go to buy, you're making a demand, which means I'm going to give you a better price for that. I'm going to try to get that price higher because the money's just not there. Now, when you go to sell it, you're increasing the supply, so your price you sell it for will be less. So it's really kind of neat that this can just happen in a liquidity pool just by changing the demand. And this is because if you're using a DEX or something else, they use what's called the automated market maker model. And that can be really susceptible to front running unless you're working that process, right? Because that large buy and large sell order will have a priority gas action to get the transaction quicker. And it takes value from the target. So you can really aim these at liquidity pools. So if you're building one, if you're building a bridge or something else that requires a liquidity pool, be really aware of that increased demand on pull. I want to buy stuff, and then a decrease in the pool's value when people want to sell large bulks. That's one of the reasons why when you see a run on the bank, it can be a real big problem for a liquidity pool. And if you're using your smart contract to back this, you just be really aware that these things are going to happen, kind of work your way around how you want to do flow control in these events. So make sure to note though, right, that your order transactions in the EVM is based on the gas price and the address, right? And you can manipulate that gas price. You can say what you're willing to pay for this, right? Using a commit and reveal schedule is the best way to approach visibility and confidentiality. Again, storing it off-chain in an array or file or a variable or whatever you want to do can help with that confidentiality of whatever's going to happen. The other thing I think is interesting too is storing the hash of the first transaction and then verify it against the second transaction. And there's a really cool library called Submarine Send. And the Submarine Send is really kind of interesting, right? Because it's an open source contract. And that's basically something you call, and you can especially work against front running attacks. It does this by temporarily hiding transactions on chain. So what it does is it will hash it, but then will salt it. So you have that salted number inside of mempool, memcache, and that's all it's going to do, right? So to anybody but the committer, the transactions are indistinguishable from anything else. You know, so you may be sending to a fresh wallet. It hasn't been used on the Ethereum chain before. So traditional commitment schemes link both the destination and the amount of money sent, making a transaction front runnable, and Submarine basically hides the wallet and the transaction. So you don't know who is going where. So it's kind of neat, and how that will work. Not sure if you want to use it, but it is an option if you just want an internal programmable library and you don't want to worry about all the work that would go into all the permutations of this. Submarine Send is just a quick, dirty way of fixing the problem. So front running, super common, right? It's any way to buy low, sell high on any item, right? It can be reduced by removing transaction ordering and using libraries like Submarine Send to kind of back up and make sure that I can't just read it out of memcache, right? It's all about using non-public data to someone's advantage in a transaction. And again, that's pulling up data that shouldn't be public, or I'm able to figure something out inside that transaction data and use it for my own purposes. And that's essentially how front running works. It's really kind of neat. There are ways of solving it in your code, and you really should. And I'll see you in the next lecture.